So in the second and third parts of this talk, I'll be presenting our empirical work. So let me start with a brief outline. In this part, I'll formulate our hypothesis and explain our finite state approach, which we introduced in our ACL 2020 paper. And in the next part, I'll compare the unsupervised finite state approach with an unsupervised sequence-to-sequence model. I'll also explain our experimental results in the error analysis that we will present in our upcoming Sigmorphon paper. So to remind you, the task is to convert informally romanized text into the conventional orthography of the language. We observe the romanized text, or what the user typed, and want to reconstruct what they meant, or the latent native script text. First of all, people resort to informal romanization when typing in the native script is inconvenient for some reason. So there isn't going to be naturally occurring parallel data for this task. People just don't type the same text in the Latin script and then again in the native orthography. So we're going to take an unsupervised approach, which means we will train our models without parallel data. As I've mentioned before, people usually substitute characters with ones that are phonetically or visually similar. And we've observed the same behavior, the same principles of similarity across multiple languages. I should also note here that my own understanding of the phenomenon is mostly informed by my experiences with Russian, which is my native language. So when I started working on this project, I thought, if it works so similarly across different languages, what if we model this shared part, this grounding, but otherwise we make as few modeling assumptions as possible? Doesn't this mean that our model will then work for any language? And of course, the answer is not really. To quote Emily Bender, this is a recipe for a linguistically naive model, not a language-independent model. There are a lot of differences between languages that you would want to account for, both linguistic and I'll call them digital here, which means having to do with how the text in these languages is encoded in our computers. I'm going to come back to this point several times in the talk, highlighting the variation between our three languages, Russian, Arabic, and Kannada. All three of those languages come from different families, and they use different writing systems. So we are going to encode these shared notions of similarity into our model as inductive bias. And we hypothesize that this inductive bias can somewhat compensate for the lack of supervision, for the lack of parallel annotated data. As I've shown before, both the visual and the phonetic similarity can be really creative and complex. So it's not easy to operationalize them and capture all this nuance. So instead of doing that, we're just going to use resources that people have built manually with the same concept of similarity in mind. I'll give more detail on this in a bit. So we're going to take a decipherment approach to this task, which means we are going to be treating romanization as a substitution cipher. Decipherment has a long history in NLP. It's been especially popularized by Kevin Knight, and it's been applied to both NLP problems and to actual code breaking problems. So here I wanted to start with this quote by Warren Weaver. When I look at an article in Russian, I say this is really written in English, but it has been coded in some strange symbols. I will now proceed to decode. So he's talking about translation here and treating translation as code breaking, which is a bit of a stretch. But if we change this quote a little and make it about informal romanization, it actually makes a lot of sense. Romanized Russian can, in fact, be considered Cyrillic Russian encoded in some strange symbols. So we'll say that our native script input has been passed through a noisy channel and came out encoded in Latin alphabet. And our goal is to reconstruct the plain text from the observed ciphertext. So now let's formalize our noisy channel model. We decompose the joint probability of the observed romanized sequence R and the latent native script sequence N into three factors: transition probabilities, emission probabilities, and the prior on the emission parameters. Because we don't actually know what the correct native script sequence is, we are going to marginalize over all possible values of N. And I'm sorry for the awkward notation here. Just wanted to say this again. N that we're summing over is not an index. It is the value of the native script sequence. So we're summing over all possible native script sequences. The emission probability should also decompose by character. But to do that, we need to know which latent characters produced which observed ones. Or in other words, we need to know the latent alignment. So we are marginalizing not just over all possible latent sequences, but also over all possible alignments between them and the observed sequence. So the prior on the emission parameters is how we encode the inductive bias into the model. And I'm going to talk about them now before we continue with the parameterization. So as I've said before, people often associate characters to some kind of out of context prototypical pronunciation, which is also often it's going to be the same as the pronunciation in context. For example, for the English letter F, we can say that the prototypical sound is F, and this is also how it's going to be pronounced in most English words. So one resource encoding such prototypical associations between a native alphabet and a Latin alphabet is a phonetic keyboard layout. So we don't need to think of how to operationalize this association. We can just read character mappings off of these keyboards. But there is a constraint. Every symbol must be mapped to one and only one key. So we are inevitably going to have spurious mappings, which I highlighted here in red for our three languages. So the spurious mappings can happen because the native alphabet is larger than 26 characters, or if there are phonemes that are in one language but not in the other. Like there is no P sound in Arabic, so the character P on the Latin keyboard gets mapped to something totally unrelated. And some of the highlighted keys here I'm showing in dashed line. See, these are the ones that are paired non-randomly. So the keyboard creator thought, if I can't pair these characters phonetically, I'll at least pair them visually or through some other kind of association, but the rest of them is just random. For the visual priors, again, we're looking for pairs of similar characters, but now we need them to look similar. So one resource that encodes this principle is the Unicode confusables list. It groups together characters that can be made indistinguishable in some fonts. So if different characters can be made to look so alike, this poses a security risk. That's something called script spoofing. Like I can take a URL and replace some characters in it with identical looking Cyrillic ones, and you can't see any difference really. But here, once I switch to another font, the difference now becomes visible. The first link has Y and P, and the second link has Cyrillic U and R. So maybe you aren't able to tell them apart in most fonts, but their Unicode representations are different. So if you click on them, they will take you to different web pages, which is something an attacker could exploit. So the message you will see here on the right is a browser warning against spoofing, which I didn't actually get when I tried to go to this fake SIGTYP link, but maybe one day when SIGTYP becomes famous, my browser starts protecting it too. So of course, this list is very restrictive. It only contains symbols that can be made nearly identical. So it doesn't capture the whole complexity of the visual substitution phenomenon. So we do get a number of mappings for Russian here, but for Arabic and Kannada, we get only a couple each. So we're not going to have enough to compile visual similarity priors for Kannada and Arabic. But there is also a spectrum of how much visual similarity is used by the speakers of those languages for informal romanization. If we imagine them schematically on the axis from fully visual to fully phonetic, then Russian would lean slightly towards phonetic, Arabic even more so, which makes sense because Arabic characters in general are less similar to Latin than Cyrillic are to Latin. And Kannada, from what I can tell, is entirely phonetic. So how do we now turn those mappings into probabilistic priors? Our conditional emission distributions are parameterized as multinomials. So here I'm visualizing this matrix of emission parameters where each row corresponds to a latent native script characters and each column corresponds to an observed Latin character. So in that case, we can create a conjugate Dirichlet prior that encodes our preferred character mappings. And mathematically, this boils down to increasing the values in the corresponding cells of the parameter matrix every time we re-estimate the parameters. The Unicode confusables list also contains mappings between groups of characters that can look identical. So here we have some examples where one Cyrillic character is mapped to 2 Latin characters. For those cases, we are going to increase the values for each of the 2 characters separately. So as I've just shown, we only have emission probabilities that correspond to 1 input character and 1 output character, because we're trying to avoid having too many parameters. So what are we going to do with the 1 to 2 or with null alignments? We are going to approximate them using insertions and deletions, which correspond to an empty character epsilon on the latent and the observed side respectively. That is, of course, a big simplification. Only the null alignments naturally match this formalization because they do actually happen by insertion or deletion. Digraphs like SH corresponding to a single phoneme should be treated as a single unit, not as a substitution plus an insertion, but this is just something we do to make the computation feasible. So note that we also added arrows between the latent states here. So now this looks a lot like an HMM, which it basically is with a lot of fancy stuff on top. So much like an HMM, our finite state model is made of 2 main components. The first one is the transition model. That's a 6-gram character level language model of the native script, which we implement using OpenGRM. And the second part is the emission model, which needs to have arcs corresponding to every possible substitution, insertion, and deletion. This is the core part of our model, and I'm going to explain it in more detail in a moment. So finally, we have acceptors for the native script or Romanized sequences, which we can compose with the emission and the transition transducers. All the training and inference computation can be done via finite state algorithms on the composed lattice. We use OpenFST toolkit to implement all of those algorithms. And the lattice is conditioned on the Romanized sequence R, which you can see here. We've done by composing with an acceptor, but we don't know the corresponding native script sequence, so we don't compose with an acceptor on the other side. Again, the emission model has to support all possible substitutions, insertions, and deletions. The simplest solution would be something like this: a single state WFST with an arc for each of those operations. Here, we're schematically representing them as a single arc, where the input can be any native character or epsilon, and the output can be any Latin character or epsilon. So this FST has a problem, which I'm going to illustrate now with a toy example. So let's say we have only 1 character I in our input vocabulary and only 1 character O in our output vocabulary. And we're trying to sum over all paths that can produce this output sequence of 1 character O. There are many paths through the lattice that could permit this output sequence. For example, you could get it from a single substitution or a single insertion or a deletion and then an insertion, or any number of deletions followed by an insertion. And clearly we can't afford to compute anything where we have to sum over an infinite number of sequences. So to avoid this infinite deletion issue, we restrict the delay of all paths through the emission transducer. Delay is the difference between the number of insertions and the number of deletions at any given time step. So this is easier to visualize if you think of it in terms of the alignment matrix, which has the input and the output sequences on the 2 sides. And every path through this matrix corresponds to a sequence of edit operations that's required to transform the input into the output. So if we cap the delay, we restrict the distance from the diagonal in the alignment matrix. For example, here, if we cap the absolute value of delay at 2, that means we are only summing over paths that fall entirely inside this highlighted band. So let's come back to our toy example. What would it look like here for this cap delay model? Again, we can just do a single substitution, where we can do a single insertion. Note that every time we do an insertion, we move to the next state on the right. Or we can do a deletion. Here we're moving to the next state on the left, and then insertion, moving right again. But we can't do an infinite number of deletions. Once we've done 2, we reach the leftmost state and we get stuck there. We can no longer delete characters until we insert at least 1. So this is the trick that we use to make the computation feasible. We use EM algorithm for training, where the E step is the shortest distance computation in the expectation semi-ring. Expectation semi-ring is like a version of log semi-ring that does the bookkeeping for you. And the M step is just normalizing the computed counts. So this exact maximization is really slow, especially if you use something like an expectation semi-ring. So we need a lot of tricks to speed up our training. We use stepwise stochastic training, which means we update the parameters after processing each batch of sequences. We do curriculum learning, where we train on the shortest sequences first. And while we train on those shorter sequences, we also prune emission arcs to make the model sparser. And we gradually increase the order of the language model in the transition transducer. And inference is just finding the shortest path through the same lattice in the max plus semi-ring or tropical. So this is the end of part 2. And in the next part, I'll talk about the data, present experimental results, and compare the 2 modeling approaches, finite state and sequence to sequence.